Hello, everybody. Welcome to the CSE 355 midterm review. We'll be going over um, some concepts such as DFAs, NFAs, regular expressions, non-regular languages, context-free grammars, push-down automata, non-context-free languages. This should be around a 16-minute review session, but it can be less than that. And then there are some concepts that if you think are wrong or are missing out on, please let me know, as some of the midterms are sort of spaced out across classes, so there might not be a lot of synergy between them, but you can always come back to this for your finals or anything because it's just more of a comprehensive review. So going over DFAs and NFAs, which are deterministic and non-deterministic finite automata. What is a DFA? It is a five-tuple, which can be defined as Q, which is the finite set of states, your finite input alphabet, transition function, which takes in any input alphabet and transitions to exactly one state per symbol, your start state, which is your Q0, and then your set of accepting or final states. A key rule in DFA is that the transition function must be total, meaning every state must exactly have one transition for every symbol. A key part of this class is understanding the difference between NFAs and DFAs. So the transitions for DFAs are exactly one next state per symbol. And then for NFAs, they are 0, 1, or many next states. There, if for DFAs, empty transitions are not allowed, and then for NFAs, they are allowed. The transition function for a DFA looks like that, where your transition function goes exactly to one specific state. And then for NFAs, your input can be the input alphabet or the epsilon, and then you can transition to a set of states or just one state. The acceptance for a DFA ends in a final state, and then the acceptance for NFA is defined as any path that leads to a final state. For DFA, the simulation is a single state tracking, and then for NFA, it tracks a set of possible states. And then expressive power is basically it can take in basically any input alphabet, so they're equal to one another. Some common exam questions that you may come across is match a DFA NFA diagram to its language. So you will be given a diagram where it's either a DFA or an NFA, and then you'll have to match it to a normal written English language description. Build a DFA for a given language over any input alphabet. You could also get trace a string through a DFA and NFA and understand if it accepts or not. Convert an NFA to an equivalent DFA. So every NFA has an equivalent DFA, but that is not the case, vice versa. Minimizing a DFA so that there's less states, and then identifying the language accepted by a given automaton, regardless of whether it's a DFA, NFA, or just a finite automaton. I wanted to go over some questions that you may get and some practice questions that you can sort of take home from this presentation. One of the questions that I decided to sort of do is build a DFA with strings ending in 0 and 1. So what I like to do is sort of write down the accept and deny strings. So that would be 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 1. 1, 1, 1, 0, 1, etc. And then the deny would be 1, 0, 1, 0, 0, etc. So what I like to do is start with the easiest accept a string and then build my DFA around that. Obviously, it won't be as easy in some of the cases, but it's always a good starting point to start with. So we know that it accepts a string that ends with 0, 1, which this specific string validates. So what I would do in this case is I would do a transition function from 0, then to Q1, then 1 from Q1 to Q2, and then I would have a loop here for 0 or 1, and I would designate that as a final state. So again, it's very nice to sort of write down your accept and deny states and then go ahead with doing that. So that's something that is useful for um, you whenever you have a um, DFA to be constructed. And then another thing that they've given is does the DFA with transition function Q0, Q1, 0, Q1, 1, and then final state Q1 except 0, 0, 1, 0. I'm just writing it down so we can all just try to solve it. Yeah, so then for this, how obviously I would solve that is we have Q0. So sort of write down your states Q0, Q1, and I think that's it. And then your transitions are given Q0 at 0 goes to Q1, Q0 at Q0 at 1 goes to Q0, Q1 at 0 goes to Q1, and then Q1 at 1 goes to Q0, I think, yeah. And then your final is Q1. So then what they're asking is, will 0, 0, 1, 0 be accepted? So sort of do like the um, computation where you go from Q0, you get 0, you get a Q1, you get 0 again, you get a Q1, you get a 1, you go to Q0, and then you go to Q1. So yes, it would be accepted. And that's like a good practice to just try and map your states together. And then this is something that you guys can sort of try and figure out. And then what language does a DFA with one state start is equal to accept and self loops on 0 and 1 recognize. For that, this question, it would basically be any language. I have the answers sort of here. So we can take that out. And since a single state is both start and accept and every symbol loops back, it accepts every possible string. So the language is all strings over 0 and 1. And then you have another question, which is basically convert um, convert this NFA with state 0, 1, 2, 3, where your start is 0, F is 3, and then you have your transition functions. And then what you would do is basically do a subset construction where you have your state 0 that goes that accepts A goes to 0, 1, and then you would basically convert these subsets into exactly one state because in an NFA you need to ensure that um, it ends up with exactly um, one state to one input. And these are some other questions that I have that you can screenshot for yourself and work on as you go by. And then going forward to our next topic is regular expressions. Regular expressions are important because basically in the exam, you'll probably get a question where you have a regular expression, and then you're basically being told to construct a DFA, NFA, or just explain how what inputs that regular expression is trying to validate or accept. So a regular expression describes a regular language using three base operations. It can be union, where it matches strings in R1 or R2, where R1 and R2 signify a specific language. Concatenation means the R2 or whatever is defined as R2 is after R1, or R1 is immediately followed by R2, and that's the condition. And then your clean star is basically matches zero or more repetitions of R. And then a quick note is epsilon matches the empty string, the empty set matches nothing, and then R plus is equal to R clean star one or more. And then the last is basically zero or one, where it's being defined with epsilon. And some exam questions that you can expect to get is write a regex for or describe language. So you could get all strings with even number of zeros, identify the language described by a given regex, convert a DFA or an NFA to a regular expression, basically eliminating states, convert a regex to an NFA. I'm unsure if this was covered, but you can always refer to the theoretical computer science textbook that's required for the class, and then simplify or prove equivalence between two regex expressions. So you would be given two different sorts of regex expressions, and then you could go over them and prove equivalence between them. So let's try and do this first one, which is regex for binary strings containing 101 as a substring. Yeah, so how I would see this question is basically 101 needs to be a substring. So again, I would try and do the accept deny strategy, where my accept would be 101 because that's still a substring. 1110100 is something. You could have 0000101 right? But then what gets denied is 01, all the single ones, 0011111000. So whenever you don't have one followed by zero followed by one as a substring, you will fail in that. Um, and then how I would sort of do it is you would have to keep this as sort of like the R1, right? So keep that, right? And then that needs to be there sort of enclosed. And then you could always have plus, right? So you can have more of that, but I'm pretty sure you can't have a clean star because that would mean that it can also be empty. And then how I would do it is 0 or 1 could be there as a clean star, and then 0 or 1 could be there as a clean star. So you're sort of making sure that 101 is a substring, and then it can be followed or not followed by 0 or 1 in any capacity. So that sort of fits what you're trying to do. And then obviously you can find another way of doing this. I may be wrong. So definitely recheck. So we can sort of go and see if this is the correct way of doing that. Yeah, so 0 or 1, clean star, 101, 0, 1. I think we could also add the plus because they haven't really mentioned that 101 can't be doubled. So I think in this solution, even though they haven't put like a plus, right? For the 101, you can still sort of do it. What language does 0, 1 describe? So let's try doing that one. And then so again, I would go the accept and deny route, and then I would try to see which ones can be accepted and which one can't be accepted. So here it says 0, so 0 and then 1 is something that I can see. I can see 0, 0, and then if I have 0, 0, 1 times 1 is something that I can see. This could also be because you have 0, 1, and then you have a clean star here, right? So you could have 0, 1, 0, 1. We could have again 0, 0, 1, 0, 0, 1. You could have absolutely nothing for 0, and then you could just have 1. So they're asking what kind of language it describes. So I would also advise to see the deny, right? So what does it not accept? So it would not accept 0, 1, 1, 1, right? Because that does not fit in the rejects. You cannot have 1, 0, 1. Um, so that's something that I can see. I could see this as a language where every 1 is followed by, every 0 is followed by a 1, right? But we can check the correct answer and see what it says. So all binary string where every 1 is preceded by 0 or more zeros. So strings that can be split into blocks, each ending in 1. So yeah, exactly, where every 1 is preceded, or you could also say how we mentioned earlier, where every 0 is followed by a 1. And then it also includes epsilon. So all binary strings can also be something, but you would have to define it in the regex properly. And then writing a regex for binary strings with an even number of 1s. So you could always, so you would basically have um two number of 1s defined in your little substring inside the regex that you could also multiply using the clean star. And then on opposite sides of the substring, you could have zeros as a clean star as well. And then converting the NFA for language L given as ABB, ABB, which would just mean 1 or more A's followed by a double B. So the regex would be A plus BB or equivalently AA clean star and then B and B. And then some more questions that you can sort of use for yourself where are these rejects equivalent? So you try to find out if they match or not, and then write a regex for strings over AB that start and end with the same symbol. So that's sort of that would come under, I think, a palindrome regex that you would have to make. And then we can move on to the next where we have non-regular languages. So an important part of this is, and I'm pretty sure that might come in some of your midterms, is the pumping lemma. So that's something that you'll have as a more comprehensive question that you could that you would have to prove. So what is the pumping lemma for regular languages? What it does, it basically assumes that an L is regular. And then there exists a pumping length P such that for every string S and L, the length of S is greater or equal to P. And then you can break S into XYZ, where Y is greater or equal to 1. XY's length is less than equal to P. And then for every I is equal greater than equal to 0, there exists a xy raised to I z in the language L. So this is important because you'll obviously get a question where the language given is non-regular, but you're going to have to use pumping lemma to prove that it is non-regular by assuming that the language is regular. So the theoretical part of pumping lemma can go as assume L is regular where pumping length P exists. Choose a specific string S in L where the length of S is greater than equal to P. Here you have to make sure that you choose cleverly. Consider all possible ways to split S is equal to XYZ. And then show that for each split, there exists some pump string, and then if you contradict every specific rule, then L is not regular. Um, so some of the common exam questions would be prove a given language is not regular using pumping lemma. Show a language is regular by giving a DFA, NFA, or a regular expression. Choose the best string S and L to use in a pumping lemma proof. So you'd be giving a language, you wouldn't have to go through the entire proof, but this would maybe come as an MCQ or something. Identify which of the several languages are regular versus non-regular, and then apply closure properties to prove non-regularity. So this is something that we can take a look at really quickly. So it says prove L is equal to 0 and 1n, n is not regular. So this is a pretty standard pumping lemma question. And then for this, the first step would be to choose your S, right? Very common to just do 0p, 1p, and then go by the rules that we had. So let's just write down the rules really quick. Where you have y is greater than 1, xy is less than equal to p, and then for every y greater than equal to 0, you have x, y, c is an L. And then you basically have to contradict that. And then we basically assume it's regular. We let P be the pumping length. We choose S is equal to 0p, 1p. And then we see that the length of S is 2p, which is greater than equal to p. And then xy, the length of xy is less than equal to p, and y consists of only zeros in that case. And then you pump, which is basically you add 2 to that xyz, and then you end up with the string shown here, which is 0 raised to p plus k, and then 1 raised to p. And since p plus k is never going to be equal to p, this is a contradiction, and L is not regular. And then you have the next question, which is prove L is equal to W, where W has equal number of A's and B's over AB is not regular. So again, a good practice is to understand which string you'll be using. So again, I think what would be a good string is S is equal to AP and BP because you have equal numbers of A's and B's. And you sort of follow the same practice that we did in the previous one. It's just different inputs. And then another question that you might get is not a language, but a regex sort of language, and then you have to prove it's non-regular. So it is not regular. You assume it's regular. You choose S is equal to 0p1, 0p1. which makes sense. And then y must be zeros only. Pumping gives us the string mentioned below, and which contradicts the language, and we can assume that it is a non-regular language. And then these are some other questions that you guys can sort of take home and screenshot on your own to understand. Going over the fourth section, this is context-free grammars, where you have your CFGs, parse trees, and derivations. A CFG is a four tuple where you have E as your finite set of variables, your finite set of terminals, your rules, where you have to define a rule, and then you have your start variable, normally chosen as S. And then below is an example given where you have your finite set of variables, such as S and A, your input alphabets, which are A and B, your rules, and your start variable. And then here, the start variable is S, and the rule is basically A, followed by S, followed by B, and then epsilon. This generates the language A raised to N, B raised to N, where N is less greater than equal to 0. It is non-regular, but a context-free language, so important thing to keep in mind that even if you have a non-regular language, it can be a context-free language. Derivation trees will be very important. So keep in mind that when you have leftmost derivation, always expand with the leftmost variable. When you have rightmost derivation, always expand with the rightmost variable. When you have a parse tree where your root is equal to S, your internal nodes is equal to variables, and your leaves are terminals. Ambiguous grammar, it means if some string has two or more distinct parse trees, and then you have your Chomsky normal form, where all rules are A to BC or A to A, which is useful for algorithms. Some common exam questions that you can get is write a CFG for a given language. Something like palindromes or balance brackets, that's very common in CFGs. Show a derivation of a string from a grammar, draw the parse tree for a string, determine if a grammar is ambiguous, and find two parse trees, convert a grammar to Chomsky normal form, identify the language generated by a given grammar. So some of the questions that we can do is a CFG for L is equal to AN BN. So, and then let me just write down other ones, and then we can solve them. And you can always just screenshot them. It's just a very theoretical, and I kind of prefer to show you guys on like drawing it out and stuff. I think it makes sense in that way. Um, yeah, and then another one is and then right, and then for A and B and you could have S is equal to ASB, right? Which could go to AABB. And this could just keep on going where you have that. So that becomes a CFG. For palindromes, that could be AABB. Sorry. So, right. So then you could have it defined as ASA, ESB, or just N with A or B or epsilon. So that covers your palindromes. And then for showing parse trees, basically what it means is trying to show equivalence. So you could start with the left parsing, the right parsing, and then these basically yield different trees, but the grammar is ambiguous. And then some other questions that you could solve that are helpful and can help you practice. One important one is every regular language also context-free, which you can say yes, where every regular language has a regular grammar, and then you can convert any DFA to a grammar. And then moving on to our next section, which is pushed on automata, which is basically NFAs augmented with a stack. Um, Definitions for a PDA is it's a six tuple. This is very important to sort of remember for each expression because they will ask you in the exam to sort of give a formal definition. So for PDA, you have Q as finite set of states, your input alphabet, your stack alphabet, which can push and pop symbols, your transition, your start state, and your set of accepting states. An important key is a PDA is equal to an NFA plus stack, and then transitions are labeled as so, meaning read A from input, pop B from stack, and push C. How the acceptance and key concepts work. Accept by final state, so the input is consumed and machine as in an accepting state, so stack contents don't matter. Accept by empty stack, so input is consumed and stack is empty, no designated accept states needed. Empty transition, so PDA can move, push, pop, stack without reading input. It's powerful for matching. And then non-determinism, meaning PDAs are inherently non-deterministic. Deterministic PDAs are strictly less powerful. Some common exam questions that you can get is design a PDA for a given CFL. So basic samples that we saw, trace the string through a PDA and show it accepts, convert a CFG to an equivalent PDA, identify the language accepted by a given PDA, and explain why a specific language requires a stack and why NFA isn't enough. So again, some of the practice questions that I have, design a PDA for some of the string that we saw before. So you would have your states such as Q0, Q1, and Q2, and the given transitions. Another question that you could get is trace AABB through the PDA. So push A per A or pop A per B. Describe a PDA for balance parentheses. Again, sort of like where every parentheses has a matching parentheses. That works for a PDA as you are able to push or pop depending on what your input is. You could also have convert the CFG to a PDA. That's integral to some of the questions that you may get. What language does this PDA accept? And then why can't a DFA recognize A raised to N, B raised to N, and why does the PDA succeed? And then the last section is non-context-free languages. So this again is a proof with the pumping lemma. It's similar to the pumping, like sort of the concept, but you would have to, it is sort of different. So again, if L is context-free, then there exists a pumping length P such that for any string in L, S, the length of S is greater than or equal to P. S is equal to UV XYZ, where VY is greater than or equal to 1. VXY is less than or equal to P, and then for any I greater than or equal to 0, that specific string is an L. So this strategy is basically you have to have 5 parts and you basically pump 2 sections simultaneously, which is V and Y. And then it's similar where you have to assume that L is context-free. You have to choose an S and you have to choose it cleverly so that you sort of can contradict all these 3 rules. Consider all splits, and then show that that specific string is not in L, and that L is not context free. And then Some common exam questions would be prove a language is not context for using the CFL pumping lemma, identify whether a language is regular, CFL, or neither, show that a CFL pumped version leaves the language, apply closure properties of CFLs, and explain why CFLs are not closed under intersection or complement. And again, I have some questions that you guys can go over by yourselves, and then prove specific languages. And then you can also find a lot of examples online where you can practice. But this sort of review was meant to sort of go over the basics and the concepts. So feel free to sort of practice without looking at the answers and see if you are correct. And then this is just a quick reference cheat sheet. I'm not sure if you guys are allowed ones, but if you are, then it's good to have some of the language classes, the machines that all of them use, the if they can have regular expressions, etc., and what the closure properties are. So that's something that I like to have. And yeah, that was some of the concepts that are important for the upcoming midterms, and I hope you guys do well. Good luck.